Hello, let's talk about time complexities, a very basic but important concept both in terms of computer science as well as interviews. Time complexity is the measure of how long a program takes to process a given input. In other words, it is a measure of how efficient a program is. Time complexities are denoted in terms of big O notation, and they're always computed for the worst case scenario for every program. Here are some of the basic time complexities that are commonly used in programs. We will talk about each one of them soon. But let's first see how you compute the time complexity of a given program. Let's talk about a linear search program, where you are given an array and you have to find if a value exists in the array or not. Since we are doing linear search, what that means is you are going to check each element of the array and see if it equals to the target value or not. Let's say you have to find target 0. So when you are doing linear search, you check first element, yes, it is equal to the target. So it works out pretty well. Seems like you only took one iteration, and for the sake of simplicity, let's call it O1 because you only did one check. But let's say if you are finding target 9, then you'll have to check each one of them and you will eventually end up checking all n elements. So that means the time complexity here is O of n. And now, since I earlier mentioned that time complexities are always computed for the worst case scenario, so the worst case that could happen here is big O of n, where the value that you are trying to find is at the last index. So that's what the linear time complexity is. And then there are some other searching mechanisms. Let's say you try to, or you want to use a more efficient searching, such as binary search, in which you do not end up checking each element. Rather, you divide the input array into half at each iteration, and then you only check in one half. So for example, if you are looking for a value 3 in this array, you will first find the mid index. You will know that the value is less than mid, so it is only in this half. So you do not check this half of the array. So on and so forth. You will keep finding the mid index and keep checking which half the value is in. So in that kind of searching, you do not touch each element of the array. Rather, you only touch logarithmic amount of elements to the base 2. So if you are not sure how binary search works, please take a look at the binary search chapter separately. All right. Now, so the basic flow, or how you can tell which program takes on or log n, is pretty simple. Let's say you have a for loop in a program that runs from 1 to n, and then it checks if each element is equal to the target value, for example, then you return true or print something. So here you are running a loop from 1 to n. But let's say you have a loop 1 to n, but you do not check each element. Rather, like I said, in binary search, you compute a midpoint and then only check in one half of the array, ignore the other half. So that will lead to the time complexity of log n to the base 2. Although we are running the loop from 1 to n, but we are not checking all the elements of the array here inside. We are only checking logarithmic amount of elements. So for example, let's say you are checking the value 4, looking for target 3. So what you will do is first you find the mid value, you find the target is here, then you find the mid value of this array, which is here, then check where is 3, then you know that this is somewhere here, then you find the midpoint again of this subarray, and then you check 3 is not here, so you check in this subarray, which is equal to 3. So you end up doing 1, 2, 3, 4 iterations to find this value, which is almost logarithmic amount of log 10. This is 10 elements, so log of 10 to the base 2 is 3.32, and it leads to about 4 elements or 4 checks. All right. Now let's say you have two for loops, a for loop which ranges from 1 to n, then you have an internal for loop which runs from 1 to n as well. So the time complexity in here is you are computing, or you are running all the elements, you are checking all the elements of the array n times, because you have an outer for loop that runs n time. So the outer for loop gives a complexity of on, the inner also gives on. So the overall is on square, on into on, because both nested for loops are running from 1 to n and 1 to n. Now let's say you had a for loop that ran from 1 to n, but an inner for loop that ran from 1 to n, but it only computed a logarithmic amount of elements of the array. Such as heap sort or quick sort. Example, so in this case, the time complexity will be big O of n for the outer loop and multiplied by big O of log n for the inner loop. So the overall time complexity will be big O of n log n, which we get in efficient sorting algorithms like quicksort, heap sort, etc. On square is a time complexity that you get, for example, in worst sorting algorithms like bubble sort, for example. So let's see where we get these time complexities before we dive into an example. So big O of 1, which is a constant time complexity, you get when you are trying to find a value by index in an array, or you are trying to look up a key in a hash map. For example, let's say we have this array 0 to 9, and you are trying to find what is the value at index 3. Now, you will quickly go check the value at 3 and it will return you the value. So why this is constant time is it does not matter what is the length of the array. Right now the length of the array is 10. It could be 100, 1 million or 100 million. The time to find the value at index 3 is going to be exactly the same when the array length is 10. So the length of the array or the n does not matter when you are computing or you are trying to find a value by index in an array. That is why it is independent of the input size, and that is why this is constant time complexity. It is going to be the same no matter what is the size of the array. Then move on to log n time complexity. This is the time complexity which we get in binary search, for example. So log n can also be of multiple different type. It could be log n to the base 2, log n to the base 4, log n to the base 8, for example, log n to the base 10, for example. So how we get log n to the base 2 is when we divide the input size into half, into 2 parts. That is when you get log n to the base 2. But if you divided the input half into 4 parts, then you would get log n to the base 4, so on and so forth.